Black holes are often described as the most violent objects in the universe, as cosmic monsters that tear stars apart and swallow everything around them. But the truth is much quieter. Black holes are not loud. They do not explode. They do not hunt. In fact, some of the strangest things about black holes happen in complete silence. Tonight, we'll calmly explore what black holes really are, not through dramatic images, but through simple ideas. We'll look at why space itself is not truly empty, why black holes are surrounded by stillness, and why time slows down without making a sound. We'll move through these ideas slowly, in clear sections, so you can follow them, or let them fade as you rest. And somewhere along the way, you may notice something unexpected. The universe does not reveal its deepest secrets through chaos, but through quiet processes that unfold patiently, far beyond human perception. When we imagine space, we usually picture emptiness. A vast black background. Cold, silent, and empty. But this image is incomplete. Space is not simply nothing. It is a physical structure, one that can stretch, bend, vibrate, and store energy. Even in the emptiest regions of the universe, where there are no stars and no planets, space is still doing something. It expands. It fluctuates. It responds to mass. This is important, because black holes do not exist inside space like objects in a container. They are changes to space itself. To understand black holes, we need to let go of the idea that gravity is a pulling force reaching outward. Instead, gravity is the way space curves in response to mass. A star bends space gently. A planet bends it slightly less. But when enough mass is compressed into a small enough region, space bends so deeply that it forms what we call a black hole. Nothing special needs to happen. No explosion is required. No sudden event announces its arrival. Space simply folds in on itself, quietly. This is why black holes are so often misunderstood. They are not objects moving through space. They are regions where space has taken on an extreme shape. And this shape has consequences, subtle, silent, and profound. One of those consequences is how black holes interact with their surroundings. Contrary to popular imagery, black holes do not constantly consume everything nearby. They behave much like any other object with mass. If the sun were replaced by a black hole of the same mass, Earth would continue orbiting almost exactly as it does now. There would be no sudden pull. No violent disruption. From a distance, a black hole is calm. This calmness extends even closer than most people expect. As matter approaches a black hole, it does not immediately fall inward. It can orbit. It can heat up. It can form glowing disks. But the black hole itself remains silent. No sound escapes. No signal announces what lies beyond its boundary. And this boundary is one of the most important ideas in modern physics. It is called the event horizon. The event horizon is not a surface you can touch. It is not a wall or a shell. It is a point of no return. Once something crosses this boundary, information about it can no longer reach the outside universe. Not because it is destroyed, but because space and time themselves are shaped in such a way that all possible paths forward lead inward. From the outside, everything appears frozen at this edge. From the inside, everything continues, quietly. This leads to one of the most counterintuitive aspects of black holes. They are not dramatic places. They are patient. Processes near a black hole unfold slowly, measured not in human seconds, but in warp time. An observer watching from far away would never actually see something fall in. The object would appear to slow down, dim, and fade, stretched across time itself. Nothing crashes. Nothing screams. It simply becomes unreachable. This quiet disappearance is not limited to objects. Time itself behaves differently near a black hole. As gravity increases, time slows down. clocks near a black hole tick more slowly than clocks far away. This is not an illusion or a metaphor. It is a physical effect confirmed by experiments even here on Earth, where gravity is weak. Near a black hole, this effect becomes extreme. Time stretches. Moments elongate. Processes that take seconds for one observer can take years for another. Yet none of this announces itself with sound or light. The universe does not mark these changes with signals. It allows them to happen silently. This silence is not emptiness. It is structure. And black holes represent the most structured silence we know. They reveal that the universe does not need noise to be active. It does not need motion to be dynamic. It does not need destruction to be powerful. Some of the most important events happen without witnesses. As we move deeper into this topic, we'll begin to see how black holes quietly alter not just space and time, but our understanding of information itself. And this leads to a question that still has no final answer. A question that sits at the edge of physics, waiting patiently in the dark. A black hole is often imagined as a kind of cosmic vacuum cleaner. Something that pulls everything toward itself with unstoppable force. This image is dramatic, but it is misleading. A black hole is not defined by what it pulls in. It is defined by how space behaves around it. To understand this, it helps to forget, for a moment, everything you associate with the word hole. A black hole is not an empty cavity. It is not a tunnel. It is not a gap in the universe. It is a region where space has become so curved that the usual rules stop working the way we expect. In everyday life, we think of gravity as a force, a pull between objects. But in modern physics, gravity is better described as geometry. Mass tells space how to curve. Curved space tells objects how to move. This means that objects are not being pulled toward a black hole in the traditional sense. They are following the straightest possible paths through a deeply curved region of space. From far away, this curvature is gentle. The black hole behaves like any other object with mass. But as you get closer, the curvature becomes extreme. At a certain point, space curves inward so sharply that all possible paths lead in the same direction. This point is what we call the event horizon. The event horizon is not made of matter. It has no thickness. You would not feel it if you crossed it. It is simply the boundary where space becomes so curved that escape is no longer possible. Even light, which always travels at the same speed, can no longer find a path outward. This is why black holes appear black. Not because they are filled with darkness, but because light that crosses this boundary cannot return. What's important is that nothing special happens at the event horizon itself. There is no sudden force, no crushing pressure, no dramatic signal. From the perspective of something falling in, space continues smoothly. This is one of the most counterintuitive aspects of black holes. The most famous boundary in the universe is completely uneventful to cross. The drama exists only for observers far away. From a distance, an object falling toward a black hole appears to slow down. Its light becomes redder and dimmer. Time seems to stretch. The object never quite reaches the horizon. It fades. From the outside, it is as if the universe quietly lets go. This difference in perspective reveals something essential about black holes. They are not places where the laws of physics suddenly break. They are places where those laws reach their limits. To see how a black hole forms, we can look at the life of a massive star. For most of its life, a star exists in balance. The outward pressure from nuclear reactions pushes against gravity, preventing collapse. But when the fuel runs out, that balance disappears. Gravity does not suddenly become stronger. It simply no longer has anything pushing back. The star begins to collapse under its own weight. In many cases, this collapse stops. The star becomes a neutron star, incredibly dense, but stable. But if the mass is great enough, even this state cannot hold. The collapse continues. Not violently, but inevitably. The matter is compressed into a smaller and smaller volume. Space curves more and more deeply. At a certain point, an event horizon forms. And once it does, the black hole exists. There is no explosion announcing this moment. No clear line separating before and after. From the outside, the process appears frozen in time. From the inside, it continues quietly. This is another reason black holes are so often misunderstood. They are not events. They are conditions. A black hole does not happen. It persists. Inside the event horizon, all paths through space lead inward. This does not mean that everything is immediately destroyed. In fact, for a very large black hole, the experience of falling in could be surprisingly gentle, at least at first. The intense tidal forces people often imagine only become extreme much deeper inside. Near the horizon of a supermassive black hole, gravity can be relatively smooth. The real mystery lies not at the edge, but at the center. At the core of a black hole, our equations predict something called a singularity. A point where density becomes infinite. Where curvature becomes infinite. Where our understanding fails. But it's important to be precise here. A singularity is not necessarily a real object. It is a sign that our current models are incomplete. It tells us that we are trying to describe nature with tools that no longer apply. In this sense, the singularity is not something we know exists. It is something our mathematics points to when pushed beyond its limits. And this is where black holes quietly challenge physics. They bring together two frameworks that do not fully agree. General relativity, which describes gravity and space-time on large scales, and quantum mechanics, which governs the behavior of the very small. Black holes sit at the intersection of these theories. They are simple in appearance, yet deeply complex in meaning. This is why physicists sometimes describe black holes using only three properties: mass, spin, electric charge. This idea is known as the no-hair theorem. From the outside, a black hole has no visible details, no surface features, no structure. Everything that formed it is hidden. In a way, black holes erase their own history. This erasure is not violent. It is quiet. And this quietness raises an unsettling question. If all details disappear behind the event horizon, what happens to the information they carried? Is it lost forever? Or does it remain, encoded somehow in the structure of space itself? This question may seem abstract, but it strikes at the foundation of physics. Because information in physics is not just data. It is the record of what exists and how it came to be. Black holes force us to ask whether the universe can forget. Before we explore that paradox, there is one more misconception to clear away. Black holes do not actively seek matter. They do not roam the universe consuming everything in their path. Most black holes are quiet residents of galaxies, surrounded by stable orbits and long periods of calm. Many have existed for billions of years without dramatic change. They wait. Not because they are hungry, but because space around them is shaped in a particular way. This patience is perhaps their most defining trait. They reveal that the universe does not rely on constant motion or noise to evolve. Some of its deepest transformations happen slowly, silently, and without spectacle. And as strange as black holes are, the space around them is even stranger. Because the closer we look, the more we realize that the most extreme object in the universe is surrounded not by chaos, but by an unexpected, almost perfect stillness. When people imagine a space around a black hole, they often picture chaos. Matter spinning violently, light tearing apart, a region filled with constant destruction. But this image comes mostly from dramatic illustrations, not from how black holes actually behave. In reality, the space around a black hole can be remarkably quiet. This may sound surprising, especially considering how extreme black holes are. But the key is to understand that silence does not mean inactivity. It means balance. Most black holes spend the majority of their existence doing almost nothing. They sit at the centers of galaxies, or drift through space, surrounded by vast regions where very little happens. Stars orbit them calmly. Gas clouds move slowly. Distances are enormous. On cosmic scales, motion itself is gentle. The dramatic images we often see, glowing disks and jets of energy, represent rare situations. Moments when a black hole is actively interacting with nearby matter. But even then, the black hole itself remains unchanged. The noise comes from the environment, not from the black hole. This distinction is important. A black hole does not produce sound. It does not emit signals announcing its presence. Sound requires a medium, particles colliding, pressure waves traveling through matter. Space, for the most part, has none of this. And near a black hole, space is often even emptier than usual. As matter falls toward a black hole, it does not plunge straight in. It tends to form an accretion disk, a flattened, rotating structure made of gas and dust. Within this disk, particles collide and heat up. They glow. They radiate energy. This is where the brightness comes from. But this activity exists outside the event horizon. The closer matter gets to the horizon, the quieter things become. From a distance, the motion appears to slow. The light stretches and fades. Signals weaken. It is not that matter suddenly stops. It is that the pathways for information grow longer and more distorted. This creates the impression of stillness. In fact, one of the most counterintuitive truths about black holes is this. Nothing ever appears to cross the event horizon. Not because it cannot, but because signals from that region take longer and longer to reach the outside world. Time stretches. Each moment near the horizon takes longer to unfold for distant observers. As a result, motion seems to freeze. The universe does not show us the crossing. It keeps that moment hidden. This is not a violent process. It is gradual, quiet, predictable. Black holes do not scream when they consume matter. They dim. They fade. They become less visible, not more. Even the powerful jets sometimes associated with black holes do not originate from the black hole itself. They are created by magnetic fields in the surrounding disk, shaped by rotation and charged particles. The black hole merely provides the geometry. It does not power the spectacle. This leads to a subtle but important idea. Black holes are not engines. They are conditions. They shape space in such a way that certain behaviors become possible. But they do not actively drive those behaviors. This is why physicists often describe black holes as simple. From the outside, they are among the least complex objects in the universe. No surface detail. No internal structure we can observe. No changing features. Compared to a star, a planet, or even a cloud of gas, a black hole is almost featureless. This simplicity contributes to the silence. There are no layers interacting. No competing forces creating turbulence. Just space, curved deeply and consistently. If you could somehow observe a black hole from a safe distance, without the interference of surrounding matter, it would be almost invisible. Its presence would be revealed only through the motion of nearby objects. Stars would orbit something unseen. Light would bend slightly as it passed. But nothing would announce itself. This quiet nature challenges our instincts. We tend to associate power with action. We expect extreme objects to produce extreme effects. But black holes demonstrate a different kind of power. The power to shape outcomes without direct interaction. The power to alter time and motion without movement. the power to hide information without destroying it. This kind of power does not need noise. It does not need constant change. It simply exists. Even gravitational waves, ripples in space-time, are not produced by a black hole sitting alone. They require motion, collisions, mergers, asymmetry. A solitary black hole in empty space would be perfectly silent forever. No signal would ever emerge. This idea is almost unsettling. An object so extreme, so central to modern physics, could exist without leaving a trace. Unless something disturbs the stillness. And this brings us to an important realization. The silence around black holes is not an absence of physics. It is the result of physics reaching a stable configuration. Everything that can happen already has. Everything that remains unfolds slowly. This is why black holes feel timeless. Not just because they affect clocks, but because they represent states of long-term equilibrium. They are not processes rushing toward an outcome. They are outcomes that persist. And yet, beneath this calm surface, something profound is happening. Because even in perfect stillness, time itself does not behave the way we expect. Near a black hole, time is stretched, reshaped, and unevenly shared between observers. The silence is not just spatial. It is temporal. Moments do not pass at the same rate everywhere. And once we begin to look closely at how time behaves near a black hole, the quiet becomes even stranger. Because time does not simply slow down. It begins to lose its meaning. We often think of time as something universal. A steady flow that moves forward at the same pace for everyone, everywhere. 1 second follows another. Clocks tick. Moments pass. This intuition feels so natural that it is difficult to imagine time behaving any other way. But near a black hole, time does not flow evenly. In fact, time itself becomes unevenly distributed across space. This is not a philosophical idea. It is a physical one. According to general relativity, time is affected by gravity. The stronger the gravity, the slower time passes. This effect is small on Earth, but it is measurable. Clocks on satellites tick slightly faster than clocks on the ground. Even a difference of a few meters in height produces a tiny change in time. Near a black hole, this effect becomes extreme. As you approach the event horizon, time slows down relative to distant observers. From far away, it appears as if time is almost stopping. But this description can be misleading. Time is not stopping in an absolute sense. It is becoming different for different observers. Imagine 2 clocks. One far from the black hole. One falling toward it. Each clock ticks normally from its own perspective. Nothing feels strange locally. The clock near the black hole does not sense itself slowing down. Its seconds feel like seconds. But when the 2 clocks are compared, they disagree. The deeper the clock is in the gravitational field, the slower it appears to run. This disagreement is not a matter of perception. It is built into the structure of space-time. Time is not a background in which events occur. It is part of the geometry of the universe. Near a black hole, this geometry is stretched. Moments become longer. Processes take more time to complete, at least from the outside. This leads to one of the most famous images associated with black holes. An object falling toward the event horizon appears to slow down. Its motion becomes more gradual. Its light becomes redder. Its signals arrive less frequently. Eventually, it seems to freeze in place. From the outside, the object never quite crosses the horizon. It simply fades. This is not because it fails to cross. It is because the information about that crossing takes an infinite amount of time to reach distant observers. The universe does not show us that moment. It hides it behind stretched time. From the perspective of the falling object, however, the experience is very different. time continues to move forward. Nothing special happens at the horizon. There is no warning, no signal. The crossing occurs without ceremony. This difference between perspectives is not a contradiction. It is a consequence of how time is shaped by gravity. Both descriptions are correct. They simply belong to different observers. This realization forces us to reconsider what we mean by now. There is no single present moment shared by the entire universe. Each region of space has its own rhythm. Near a black hole, this rhythm slows dramatically. Moments stretch. Sequences elongate. Time becomes less like a flowing river and more like a landscape. You do not move through it so much as a long path shaped by gravity. This quiet stretching of time has subtle consequences. Processes that appear frozen from afar may be unfolding smoothly locally. Events that seem to take forever may be completed quickly from another perspective. There is no universal clock keeping everything in sync. The universe does not enforce uniformity. It allows time to behave differently in different places. Black holes represent the most extreme example of this flexibility. They show us that time is not a fixed backdrop. It is responsive. It adapts to mass and energy. It bends along with space. This bending does not require motion or sound. It happens silently. And it happens continuously. Even far from black holes, time is never perfectly uniform. Gravitational fields overlap. Space-time is gently curved everywhere. The differences are usually too small to notice. But near a black hole, they dominate experience. The future itself becomes uneven. This has a strange implication. If time flows at different rates in different places, then the sequence of events is not absolute. Cause and effect remain intact locally. But globally, there is no single ordering that applies everywhere. The universe does not keep one master timeline. Instead, it allows many overlapping timelines, each shaped by local conditions. This idea can feel unsettling. We like to imagine time as something reliable and consistent. Black holes show us that it is not. They reveal that time is as dynamic as space. And just as space can curve, stretch, and fold, so can time. Yet despite this complexity, the experience remains calm. There is no turbulence in time, no oscillation, no vibration, just gradual distortion. This is why the slowing of time near a black hole feels so quiet. Nothing announces it. Nothing marks the transition. It simply becomes harder and harder to compare moments between different regions of space. Time does not break. It drifts apart. And as time becomes less shared, another problem quietly emerges. If time behaves differently for different observers, what happens to information? If signals slow down and fade, does the universe keep track of what has happened? Or does something get lost along the way? This question leads directly to one of the deepest puzzles in modern physics. A puzzle that has nothing to do with motion or sound, and everything to do with memory. In everyday language, information sounds abstract. It feels like something related to data, messages, or knowledge. But in physics, information has a very specific meaning. Information is not what you know about something. It is what exists about it. The exact arrangement of particles, their positions, their motion, their relationships to one another. If you know the complete information about a physical system, you could, in principle, describe it perfectly. This idea is so fundamental that it is built into the laws of physics. According to everything we currently understand, information cannot be destroyed. It can change form. It can spread out. It can become difficult to access. But it cannot simply disappear. This principle underlies conservation laws, predictability, and the continuity of physical reality. And this is where black holes create a problem. When something falls into a black hole, it crosses the event horizon. From that moment on, no information about it can reach the outside universe. Not its position, not its structure, not its internal state. From the outside, all details are lost. The black hole appears to contain only mass, spin, and charge. Everything else is gone. This seems to suggest that information has been destroyed. And that creates a contradiction. On one hand, quantum physics insists that information is always preserved. On the other hand, black holes seem to erase it completely. Both frameworks are extremely well tested. Both work with astonishing accuracy in their own domains. Yet here, they disagree. This disagreement is known as the black hole information paradox. It is not a minor issue. It strikes at the consistency of physics itself. If information can be destroyed, then the universe is not fully predictable. If it cannot be destroyed, then black holes cannot behave the way we think they do. Something has to give. To understand why this is so troubling, imagine a simple example. Suppose you burn a piece of paper. The words disappear. The paper turns to ash and smoke. At first glance, the information seems lost. But in principle, it is not. The smoke, the ash, the heat, all of it still carries the information in a scrambled form. If you could track every particle perfectly, you could reconstruct what was burned. The information is dispersed, not destroyed. Black holes appear different. When something falls in, there is no known way for its information to escape. It does not spread out. It does not transform into something observable. It simply vanishes from view. For decades, this puzzled physicists. Some propose that information is truly lost. Others argue that our understanding of black holes must be incomplete. Slowly, a different idea began to take shape. What if the information is not lost, but hidden? What if it is stored at the boundary of the black hole, rather than inside it? This idea suggests that the event horizon is not just a passive boundary. It may carry information. Not in the way a hard drive does, but in the way a surface can encode patterns. This led to a surprising proposal. That the information about everything that falls into a black hole is somehow encoded on its surface. Not inside. On the horizon itself. This idea is deeply counterintuitive. It suggests that the three-dimensional contents of a region can be fully described by information stored on a two-dimensional boundary. This concept is known as the holographic principle. The name comes from holograms, where a flat surface contains all the information needed to recreate a three-dimensional image. In this view, black holes are not information destroyers. They are information compressors. They take complex systems and encode their details in an extremely compact way. Nothing is lost. But almost everything becomes inaccessible. Even more strangely, black holes are not completely black. Over very long timescales, they emit a faint radiation. This is known as Hawking radiation. It arises from quantum effects near the event horizon. The radiation is incredibly weak. For most black holes, it is far colder than the surrounding universe. But over immense periods of time, this radiation causes black holes to slowly lose mass. Eventually, they evaporate. This raises a new question. If a black hole disappears, what happens to the information it contained? Does it escape with the radiation? Or is it lost when the black hole is gone? Early calculations suggested that Hawking radiation carried no information. It appeared random. If that were true, information would indeed be destroyed. But this conclusion created even deeper problems. Over time, evidence began to suggest that the radiation may not be entirely random. That subtle correlations could encode information after all. If this is correct, then information slowly leaks out of black holes. Not dramatically, not suddenly, but quietly, over unimaginably long times. In this picture, the universe never forgets. It just takes its time remembering. This resolution is still not complete. Physicists continue to debate exactly how information is preserved. Different models offer different answers. But what matters here is not the technical details. It is the shift in perspective. Black holes are no longer seen as places where reality breaks. They are places where reality hides. They challenge us to rethink where information lives. Not inside objects, but at boundaries. Not in volume, but in relationships. This idea has influenced far more than black hole physics. It has reshaped how we think about space, time, and the structure of the universe itself. All of this complexity arises from something that appears perfectly simple. A silent region of space. A smooth boundary. No signals. No motion. Just a quiet question about whether the universe is capable of forgetting. And as we try to answer it, we are led toward an even stranger realization. That what we call empty space may be far more active than it appears. When we hear the phrase empty space, we tend to imagine nothing. A complete absence. No matter. No activity. But in physics, empty space is never truly empty. Even in regions far from stars, planets, and black holes, space is filled with subtle activity. It may not contain particles in the usual sense, but it is not inert. According to quantum physics, space is a dynamic field. Energy fluctuates. Pairs of particles briefly appear and disappear. Fields vibrate quietly at every point. These processes do not produce light or sound. They do not announce themselves. But they are always happening. This means that what we call vacuum is not a static background. It is an active medium. One of the simplest ways to see this is through the concept of zero-point energy. Even at absolute zero temperature, when all classical motion should stop, quantum fields still retain a minimum level of energy. They cannot be completely still. This restless nature of space has measurable effects. It can influence the behavior of particles. It can shift energy levels in atoms. It can even produce forces between objects placed very close together. All of this happens without motion in the traditional sense. Without noise. Without visible change. The universe is quietly busy. Black holes magnify this truth. They show us what happens when the structure of space becomes extreme. But the underlying principles exist everywhere. Space responds to mass. Time responds to gravity. Information responds to boundaries. None of this requires dramatic events. It unfolds continuously. Even the expansion of the universe itself is silent. Galaxies move away from each other not because they are traveling through space, but because space between them is stretching. There is no center, no edge, no sound. The distances simply grow. This expansion is not felt locally. Atoms remain the same size. Solar systems stay intact. The change occurs at the largest scales, beyond direct perception. This is another example of how the universe changes quietly. The most significant transformations often leave no immediate trace. They do not disrupt everyday experience. They simply accumulate. Over time, these subtle effects shape everything. Stars form. Galaxies evolve. Structures emerge. All without a guiding hand. Just the quiet interplay of simple rules. Even emptiness follows laws. This realization shifts how we think about silence. Silence is not the absence of activity. It is the presence of activity without signals. Processes that do not announce themselves. Patterns that do not demand attention. Black holes represent the extreme version of this idea. They are not places of chaos. They are places where structure becomes so deep that it hides its own processes. The same is true, in a gentler way, of empty space. We move through it constantly, unaware of its complexity. Our bodies pass through quantum fields. Our atoms exist in a vacuum that is never still. Yet we feel nothing. The universe does not overwhelm us with its details. It allows us to exist at a comfortable scale. Only when we slow down and look carefully do these quiet paradoxes become visible. And when we do, a pattern emerges. The universe does not rely on noise to function. It does not rely on spectacle. Its most fundamental processes are subtle, stable, and patient. They operate continuously, without urgency. This perspective offers a different way of thinking about cosmic extremes. Black holes are not exceptions. They are part of a continuum. They follow the same principles as empty space, only pushed to their limits. What changes is not the nature of reality, but our ability to observe it. At certain boundaries, information becomes inaccessible. At certain scales, time becomes uneven. But nothing truly stops. Nothing truly disappears. It simply becomes harder to reach. In this sense, the universe is not a place of sudden endings. It is a place of gradual transitions. From activity to stillness. From visibility to invisibility. From simplicity to depth. All connected by the same quiet rules. And as we take one final step back, a broader picture comes into view. Black holes, empty space, and the flow of time are not separate mysteries. They are expressions of the same underlying structure. A structure that does not shout. It does not rush. It waits. As these quiet processes continue, there is nothing you need to hold on to. You don't need to remember every detail. You don't need to follow every idea. The universe does not ask for constant attention. Black holes will continue to exist whether they are observed or not. Space will continue to fluctuate whether it is measured or not. Time will continue to stretch and flow in its own uneven way. Nothing depends on your awareness of it. This is one of the most common truths hidden inside these ideas. Reality does not require effort. It unfolds according to simple rules, applied patiently across vast scales. Even the most extreme objects in the universe do not rush. They do not announce themselves. They simply remain. As you listen, you may notice how the ideas begin to blend together. Black holes become less like objects and more like regions. Time becomes less like a sequence and more like a landscape. Space becomes less like emptiness and more like a quiet structure holding everything in place. There is no need to separate these thoughts. They are already connected. Just as the universe does not draw sharp lines between moments, you don't need to draw sharp lines between ideas. You can let one thought fade into the next. If your attention drifts, that's fine. The information does not disappear. It settles. Much like matter approaching a black hole, ideas do not vanish. They slow down. They stretch. They become quieter. And eventually, they move beyond the point where they need to be followed. The universe does not resist this. It allows things to pass naturally from one state to another. From motion to stillness. From clarity to rest. Even empty space is never truly empty. And even silence is never truly still. Processes continue quietly, whether they are noticed or not. You don't need to stay awake to understand them. They will continue without you. So if your thoughts begin to soften, you can let them. If your focus loosens, you don't need to pull it back. The universe is not going anywhere. Its deepest structures operate slowly, patiently, and without urgency. You can rest inside that patience. You can let the details blur, knowing that nothing important is being missed. Somewhere, far beyond perception, space is curving. Time is stretching. Information is being carried forward in ways we do not yet fully understand. And none of it requires effort from you. You can simply remain here for a moment. or let the moment pass. Both are perfectly fine.